In this video, we'll look at the question, what does it mean for a function to be smooth? Some graphs are smoother than others, so there's some kind of a hierarchy of degrees of smoothness. I hope you have watched the previous video on complex numbers because although our topic is real analysis, we need to refer to complex theory for a complete explanation of what's going on here. Our first example. From real analysis is a function g, as shown, that is differentiable, but the derivative of g is not continuous. When x is not 0, we know how to take g prime of x. At least 99% of our calculus students can do this. How many calculus students know how to take g prime of 0? This should be more basic. You have to go back to the definition, but here probably about 1% of calculus students actually remember how to do it. You go back to the definition of a derivative. Can't I just take the g prime of x and let x equal 0? Well, no. Can I take that expression and somehow take a limit as x goes to 0? No. That's the point. The limit does not exist, but the derivative does exist. Oh, you mean I have to use the definition? Yes, you have to use the definition. So here's the definition, g prime of 0. It's this limit, and now it simplifies to this, and the limit is 0. You'd use the squeeze theorem for this, right? The sign oscillates between plus or minus 1, and h goes to 0, so that forces the limit to be 0. Let me fill in that missing value in the formula for g prime of x. So we have a function g that I have the derivative, and the derivative is defined everywhere. G is differentiable everywhere. But the derivative is not continuous. The limit of g prime as x goes to 0 does not even exist. An important example to keep in mind, and in real analysis, we're concerned with a kind of hierarchy of degrees of smoothness for functions. So in this big bubble, I'll look at all the functions that are continuous. This is a class of functions that we call C0 or C0 of R. And then inside that, we have a smaller subset consisting of functions that are differentiable. Differentiable is stronger than continuous. Differentiable implies continuous, but not conversely. And inside that, we have an even smaller class that we call C1. These are the functions that are continuously differentiable. Well, I just showed you an example. Our function g is differentiable, but not continuously differentiable. And you can see maybe where we're going with this. So for every n, we can talk about the class of functions Cn, which is the class of all functions that have an nth derivative, and the nth derivative, moreover, is continuous. Now, within the class of C1 functions, continuously differentiable, we have functions that are twice differentiable. That's the next level of smoothness. Inside that, we have continuously twice differentiable, and then 3 times differentiable. So we're getting smaller and smaller classes, and you can keep going. There's an infinite number of levels to this hierarchy, all the way down to the class of C infinity functions, which is the class of functions that are infinitely differentiable, meaning you can take the derivative as many times as you want, once, twice, 3 times, and so on. Now these, surely they're what we would call really smooth functions. In a given context, people might require some different degree of smoothness, maybe not this much. So the point is there's not just one notion of smoothness. This is really smooth. But, once you have a smooth function, then that's not as far as you might want to go. Because for a smooth function, that means you can write down all the derivatives, and then you can take the derivatives and evaluate them at 0, and therefore write down the Taylor series. But what does that tell you? You've got a Taylor series for the function. Is it going to converge? Is it actually going to converge to the original function that you started with? And that's not a given. So in a small interval, you might hope that at least that's true. So let me talk about what an analytic function is. So in our previous video, we showed a function, f, that had a Taylor series converging between -5 and 5. As an example of a real analytic function, it's not only C infinity, which means infinitely differentiable, but it's also analytic. And I showed you the Taylor series centered at 0. You can find the Taylor series centered at every point, and it's going to converge in some interval around that point. And that's what it means to be analytic. So at every point of the domain, you have a series that converges in some interval to the function. So that was an example of a C infinity function that passes the final test of being real analytic. However, in real analysis, there are functions that are C infinity, but not analytic. So the Taylor series does not converge to the original function, and that I'll get to an example of that in a moment. But it's a phenomenon that really is problematic in some ways. You could call it beautiful or problematic, depending on your point of view, but it is distinctive of studying real analysis. I want to point out that for the complex numbers, this is all much simpler, and you don't have to worry about this kind of thing. In fact, for functions from the complex numbers to the complex numbers, once it's differentiable, then it's analytic. So this whole hierarchy, if you like, collapses. This huge infinite hierarchy, in the case of complex analysis, simplifies to just analytic or not. So, that's it. So it's part of why I say the complex analysis is the opposite of complicated. I mean, it really is much simpler than real analysis. To get to my example, I want to motivate that by asking the following question. I want to build really smooth functions. And let's say I want a function that transitions from a constant value 0 up to a constant value 1. I'm doing this over the reals. And let me show you an example of what I mean. So I can transition from 0 to 1 in a very crude way by just a step function with a jump discontinuity that just jumps from 0 to 1, like in this graph. The function jumps from a 0 on the left side to 1 on the right side. It's not even continuous, so that's not good for me because I was hoping for a smooth function. So I guess I'm going to try to do better by ramping up from 0 to 1 over some interval. And I can use this piecewise linear function to do that. I take the function which goes from 0 to 1 with a line segment in between. This is continuous. So that's okay. It's better than my previous example as far as I'm concerned. And this function is C0, meaning it's continuous, but it's not differentiable. Now, if I were designing a skateboard ramp or an on-ramp for an interstate highway, then probably this is not good enough for me. I want a shape that's more smooth. So let's try to do that. Here's something that does better. This function is not piecewise linear, it's piecewise polynomial. And so I ramp up from a constant 0 to a constant 1, where in between I have this cubic. And I have designed this cubic so that at the transition points, the values agree and the derivatives agree. So this turns out to be differentiable. In fact, continuously differentiable. So this is a C1 function. But if you go through the details, I encourage you to check, then you'll see that you cannot take a second derivative. The second derivative at 2 points does not exist. So this is a little bit better, so it's more smooth. But here's something that does even better. This one manages to be continuously twice differentiable. So this function is C2. But it's not 3 times differentiable. Please, as an exercise, you should look at the first and second derivatives and try graphing them and see what's going on. Pause the video and try that. Now you start to get the idea. So we can design a sequence of piecewise polynomial functions, each one smoother than the one before, and transitioning from constant 0 to constant 1 with higher and higher degrees of smoothness. Now, how far can we push this idea? So all my examples are just going to give me Cn for higher and higher values of n. Can you do this with a really smooth function like C infinity? Can you get an infinitely smooth function, infinitely differentiable, that transitions from constant 0 to constant 1? Well, yeah, in fact, you can. You can do that, and I'll show you an example at the end. But it turns out that this thing that you get will not actually make the final step of being analytic. And the reason we get stuck has to be explained using complex numbers. If you go a little ways off the real line and let x just get off the real line into the complex numbers, you see that there's something really strange happening. So before we get to that, I need to start with a different example. This is a function that I will call e of x. And my function e of x has this graph. It's hard to really portray it well by looking at the graph from the computer because everything is happening so close to the origin. But near the origin, the function really flattens out, almost really perfectly flat at the origin. So it's an example of really extreme flatness, amazing flatness. The function has value e to the minus x squared if x is not 0. When x is 0, you just stick in a 0. Otherwise, you'd have a discontinuity there. So you put in a 0 to remove the discontinuity. And now you can work out the derivative. Go back to the definition. So here is e prime of 0. It's this limit by definition. And if we allow you to use L'Hopital's rule, and you can work out what the limit is and get the correct answer, which is 0, I will fill that into the formula for e prime of x. Now, unlike my original example with the function g from the beginning, you can actually keep going. So you can take a second derivative, the derivative when x is not 0. Now again, you still have to go back to the definition to get e double prime of 0. This time e double prime of 0 from the definition, so that's this limit. It's the derivative of e prime at 0. And again, you can use L'Hopital's rule to evaluate this limit. And again, you should get 0. I'll fill that into the table, and then e triple prime, it starts to get more complicated, but you can see where this is going again. You can work that out. It's the derivative of e double prime at 0. You need the definition of derivative. There's no other way. You have to use the definition of derivative. And then you can use L'Hopital's rule to work out that limit, and here it is. And if you keep going, then you'll find that the function is infinitely differentiable. Now I'll talk about an inductive proof a little further along in the course. By induction, you can show every derivative is 0 at the origin, all the higher order derivatives. And what this means is that the function not only has a horizontal tangent, but all the higher order curvature goes to 0 at the origin. That's a way of saying it's just extremely flat at that point. Everywhere it's perfectly smooth in the sense of C infinity, and at this one point, it's extremely flat. So here's a cool thing you can do. You can do kind of surgery on our previous example by stitching together a flat function with 0, constant 0 on the left-hand side, and on the right-hand side of the graph, we just replace by the previous function that I called e of x. And if you take this function, then it's still going to be C infinity, meaning it's infinitely differentiable. That's because on the left half of the graph, all the function values and higher derivative values, they all perfectly match up with what happens on the right-hand side. Because you know the only point of question is at the origin, and you've guaranteed that everything matches up at that point. So the resulting function I'll call e tilde is perfectly smooth, as the previous example e was, and infinitely differentiable, and it's also perfectly flat at the origin. But on the right-hand side, the function is positive. On the left-hand side, it's 0. So this is kind of weird. So as I've said, all the derivatives are 0 at the origin, just like the original function e was. So what's the Taylor series for this function? All the derivatives at the origin are 0, and if you substitute them in, then the Taylor series has all its coefficients 0. And so that means the Taylor series is just 0. And this, by the way, is the same thing as the Taylor series for the e of x from the previous example. So I have two different functions with the exact same Taylor series. So you can actually have lots and lots of different functions that have the same Taylor series, because as it turns out, the Taylor series doesn't really depend on the entire graph of the function. All it really depends on is what's happening really close to that point. In this case, the Taylor series centered at 0, so it really only depends on the higher order derivatives at 0. We have several different functions having value 0 for every derivative at the origin. I must point out that although the Taylor series exists and the Taylor series converges, nevertheless, the Taylor series, what it converges to, is not the original function. Well, except at 0. So at 0, everything is 0. But apart from that, you're not going to get the function you started with. So you can have a Taylor series that converges, but what it converges to is not the original function in any positive interval around the point. So this is evidence that our function is not analytic, because we don't have any positive radius interval around 0 where the series converges to the original function. So this function is infinitely smooth in the sense of C infinity, but it's not analytic, meaning that its Taylor series does not converge to the original function e tilde of x. So this is what I was referring to before about this hierarchy. You get to smoother and smoother functions, you get all the way to C infinity functions, but then it's another step to get to analytic. And this function doesn't cross that point. It's C infinity, but it's not quite analytic. Now I'm going back to my original motivating problem. I'm now able to construct this function I'll call f infinity of x. And this is a really smooth transition function from constant 0 to constant 1. I can just splice together, and you can convince yourself that the denominator here is always positive. So all the formulas for taking derivative work. You don't have to go back to the definition of derivative. You can just use your formulas like quotient rule repeatedly and keep taking derivative forever. So it's C infinity. And you can also look at this function and see why it has constant 0 on the left, constant 1 on the right. So it's one way to construct an infinitely smooth function, like I promised you at the beginning of this video. Infinitely smooth, transitioning from constant 0 to constant 1. Although this function is infinitely differentiable, it's not analytic. And to understand why, you need to look at what's happening when the real variable x is replaced by a complex variable z, which lies just off of the real line. And although the function is infinitely smooth on the real line, if you just move away, the function becomes extremely ill-behaved, really wild, really convoluted in its graph, oscillating wildly over huge values in every direction in the complex sense. The origin is, in fact, much worse a kind of singularity than the pole we had in our previous video. This is something called an essential singularity. This is unavoidable if you're looking for any smooth transition between two different constant values. The function just is not even differentiable in a complex analytic sense at the origin. So over the real numbers it is, but over the complex numbers it's not. So you're not even getting into that hierarchy at all in the complex analytic sense. It's not complex analytic. So that's why you don't have a Taylor series converging to the function in the complex setting.